Alright, P series. We're still in 10.4. The integral test is used to analyze the convergence of an entire family known as the P series. The P series looks like this, and we did a problem having to do with this just a few sections ago. It's called the P series, and it's all of the terms where the P is the power. And so example 3 wants to know, for what values of P does the series converge? Now we've already done this, but we'll do it again. It said, first off, notice that when P is equal to 1, then this summation is just 1 over K, which is the harmonic. So we know it diverges. Okay, now let's talk about the rest of it. This function is decreasing. It is always positive. It is continuous from 1 to infinity, so we're good with that. And so we're going to look at the integral. Now let's just look at the integral from 1 to infinity, and let's talk about x. It'd be x to the negative p dx. And the integral converges, they're going back, it's section 8.8. So if you look at this, if the p is greater than 1, then this is going to be 1 over x to some positive number. Let me rewrite it. 1 over infinity to k to the p. And so if p is greater than 1, then this is 1 over x to some positive number, and I would raise the power, flip it in front, and it's going to converge because it's going to keep getting tinier and tinier and tinier. And we did this in section 8.8. This converges. But if we look at when p is negative, or p is less than 1, this was p greater than 1, this is p less than 1. If p is less than 1, if we think about this, that would mean that when I bring it up here, x to the negative p, that would be x to a positive number. And x to a positive number, as you stick in infinity, is going to grow without bound. This is going to go to infinity, so it diverges. Okay? This guy is going to go towards some number. So, the rule that we've got here for the P series is that, and it's example 3 and also the theorem, we just proved it, that in a P series, the summation k equals 1 to infinity of 1 over k to the p converges for p greater than 1 and diverges for p less than or equal to 1. This is a good theorem because it tells you when it converges and when it diverges. And in contrast to the divergence theorem, which only gives you information about the divergence. So example 4 now, 3 was actually proving the theorem. Example 4 wants us to use a P series. So this is the summation k equals 1 to infinity of 1 over the 4th root of k cubed, which actually is the summation k equals 1 to infinity of 1 over k to the 3/4. 3/4 is less than 1. So according to my rule, the series diverges. And this would be by P series test. That was part A. Part B, now we've got a summation k equals 4 to infinity 1 over k minus 1 squared. Okay, so let me fix it a little bit. Let's rewrite it, because I don't know how to work with the k minus 1 in there. If I could fix this to give me, actually before I do that, let me write out some terms. When k is 4, I would get 1 over 3 squared plus 1 over k is 5, 4 squared plus 1 over 5 squared plus dot dot dot. So let's make it a different series so that it turns out just to be 1 over k squared. I would have to start my series at 3 for it to give me that same set of answers. So now I'm looking at it, and it's a p series with p equal to 2. 2 is greater than 1, so this series converges. By the p series test. It may bother you because it looks like we added an extra term, but we really didn't add an extra term because it's going on to infinity, so it doesn't affect the outcome of the convergence. All right, example 5, and this is going to use the theorem on estimating a series with positive terms. So make sure you read that material before trying to do problems like this. How many terms of the convergent p series summation k equals 1 to infinity of 1 over k squared must be summed to obtain an approximation that's within 10 to the negative 3 of the exact value? Okay, so according to that theorem, the remainder is less than the sum from n to infinity of f of x dx, which in our case would be n to infinity of 1 over x squared dx, which if I integrated that, raise the power, flip it in front, I'd end up with 1 over n after I plugged and chugged, because I'd have from n to infinity, and 1 over infinity would be 0. So I would get that. Now, to ensure that that's going to happen, we've got to have r sub n has to be less than 10 to the negative 3. So we have to choose n so that 1 over n is less than 10 to the negative 3. Which means if I flip it over, that means n is greater than or equal to 1,000. So you have to sum up at least 1,000 terms of the series to be sure that the remainder is less than 10 to the negative 3. And that's part A. Let's look at part B. Find an approximation to the series using 50 terms. Okay. So we are going to, using the bounds on the series itself, we're going to come up with a lower bound and an upper bound, where s is the exact value of the series. So we know the lower bound is going to be, let me write it like this, s sub n plus 1 to infinity of dx over x squared, which would be equal to s sub n plus 1 over n plus 1. And then the upper bound is going to be s sub n plus the integral of n to infinity of dx over x squared, which would turn into, this is an integral sign, it kind of looks like the s's, s sub n plus, this would turn into 1 over n if I integrated and plug and chug. So what have I got? I've got s sub n plus 1 over n plus 1 is less than the exact value, which is less than s sub n plus 1 over n. Using the calculator to sum up the first 50 terms, which means you have to find the summation button on your calculator, we get s sub 50 is equal to approximately 1.625133. So now I'm having to put that in here. I want 50s for n, so it's going to be, I don't know if I can fit it on here or not. Let's see. I'm going to write it over here. So that's going to imply that s sub 50 plus 1 over 50 plus 1 is less than or equal to the exact answer, which is going to be less than or equal to the sum of 50 plus 1 over 50. Oops, that's a 50 right there. And if I plug it all in the calculator, s sub 50 is that 1.6 number. So I'm going to get 1.6, if I add 1.625133 and 1 over 51 together, I get 1.644741 is less than s is less than If I stick in the 1.625133 plus 1 over 50, I get 1.645133. Now let's take the average of these two, because S is somewhere between them, as our approximation, and you get an approximation for S of 1.644937. And they have figures to illustrate this. They zoomed in on it so you can see what's happening to it. But you get your boundaries and then you take an average to get your approximation. And that's the end of number 5.